Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. So for today's podcast, we've got a really interesting episode lined up. This is a technology area that I'm asked about all the time. So I get questions on a very, very regular basis asking me for the sort of future prospects, what's happening and when will we see it on the market. And of course, that's solid-state batteries. So we're very, very lucky to have John Tinson from ilika, who's agreed to join us and talk to me about solid-state batteries. So good morning. Good to have you here, John.
Good morning, Ryan. A real pleasure to be on your podcast.
And actually, people will notice, hopefully, that the audio quality is slightly better than usual. And John is actually here in the flesh. So we're properly face-to-face. So hopefully the audio will work out a little bit better this time. So John, if we could just get started and tell us a little bit about your background and
Sure.
how you came to be doing what you do now.
Yes, as ever, it's a journey that's, okay, I'll explain. The physics was the subject, so I went to Birmingham University to study physics, and really with no great understanding of being a scientist. It was more about, it seemed a very useful kind of degree that could be put to many different purposes. Yeah. But I was quite a commercial person even then, so the intention, I guess, was to move in a commercial domain with that physics degree. And that's pretty much what happened. I came out and went into actually test and measurement. Some of older viewers may remember AVO, amps, volts and ohms,
okay.
or even mega. And actually I was African sales manager for about 4 or 5 years, which is great as a young person, being the ability at that age to travel around virtually every country in Africa.
Oh, wow.
Trying to intercept sort of government funding and do the electrification and telecommunications of African countries. And I say it was a great sort of grounding in export. And over the few years, did a number of other regions, Latin America, the Middle East, etc. So that was a lovely start to a selling career. And it's always been, for me, about international, and it's always been about batting for Britain, I guess, taking British technology and getting it placed overseas. From there, though, 5 or 6 years after that, went on to a company called CFAM, which is photonics in particular.
Okay.
And here, I guess, more using the physics side of things, we were looking at subsea. This is the days where I guess the internet was just coming through. We needed to solve the repeaters issue of how you would take a signal from the UK to America. At that point, I guess you could only electronically repeat every 100 or so kilometers. So there's many repeaters across the Atlantic.
Yeah.
But with photonics, the idea was every 600 kilometers. So dramatically reducing. And the key thing is, could you keep the signal in optics and not take it out of, you had an optical cable, could you take it sort of and amplify it in optics? Now, as it happened, and as a sort of it connected later on, Pirelli in Southampton were working quite a lot in that space, I was in Torquay at a company called CFAM, but there was technology called the erbium-doped fiber amplifier that was being created for this sort of photonics.
That rolled off you. The erbium-doped
fiber amplifiers is a way of amplifying fiber optics light within the fiber.
Oh, wow. Okay.
So we worked on components. We were working on tap couplers and multiplexers at CFAM, but did very well. So well, in fact, that it was bought for a large sum, and life moved on. So the next for me was actually up in Rothesay, of all places. So this was a move from Torquay, where the CFAM company was, up to Rothesay in Scotland. And here it was cabling. It was a mixture of optical and copper cabling. But my business unit that I headed up at this time, I was about a 60 million. Well, it was started off smaller than that, but about £30 million business unit, part of BICC, British Insulated Calendar Cables.
Yeah,
the company is called Brown Rex, and what a good time to arrive, because we had a optical capability at a time when the world wanted an optical capability.
Yeah.
So we sort of created a telecom unit within my business unit, and we went crazy, doubled the turnover from 30 to 60. And this was at the time when we were rolling out across the canals and railways and roads of the UK,
Right.
Optical cabling. But also we were in our business unit putting copper cabling onto things like the Astute class submarines, the Type 42 destroyer, the Eurofighter, and also some catalytic converters into cars. So very interesting time. We were doing effectively it was a specialty cabling business unit.
Yeah.
And so you got involved in lots of interesting projects. And
a big move from, so talking at one end of the country to then Rothesay at the other end, that's quite a big change.
I was helped there. My wife had been educated in Edinburgh and had friends in Edinburgh. We moved to South Queensferry, which is just across the bridge from Edinburgh. Yeah. So it felt pretty comfortable. I did have 2 young girls at the time, and so they were preschool age, so it's not so hard to move them up. And we were moving up to people we knew. And my mother was from Edinburgh.
Okay. So there's family link.
There's family there. So it was a good time. And I'm a particular keen hill walker, and I like climbing. So what's not to like about a playground called the Scottish Mountains?
Yeah, fantastic. A little bit cooler than.
We did notice that. We didn't use our back garden very often.
Right. Yeah.
So again, 5 or 6 years in this environment. But telecom then went into reverse. This was the sort of the crash, I guess, 2003, 2004. At that time, there was a bit of hell of a dip in that sector and in many other sectors as well. So the company was downsizing quite dramatically. It'd already been sold. BACC had sold it to a company called Novar, now part of Honeywell. Yeah. But the company was downsizing, and I began to look for what my next opportunity might be. And I was headhunted at this stage, a company in Hedge End in Hampshire, who were just forming, or actually had formed, but they were repurposing. And this was a company called SPI, which was a photonics company. And their idea, and this is where the sort of circle met, was that you could use this technology for erbium doped fiber amplifiers, but actually you could create a laser from it by putting Bragg grating mirrors on either end of the amplification stage. Yeah. You could then create a laser. And the point was being lasers at that time were instruments of last resort in the manufacturing sense. If you wanted to cut metal, weld metal, or mark things, you tried it every other way, and if you couldn't, then you used a laser. And that's because you needed sort of PhD guys fiddling with mirrors to operate lasers on factory floors. So the plan was to create a black box solution that needed no maintenance. It was a sealed unit.
Right.
Only 2 companies in the world had the technology. This was the intellectual property that we got out of Southampton University, but there was a Russian company called IPG Photonics that also had their technology. A guy called Valentin Kapontsev, so there's only 2 people doing this, and very early stage activity. We created those lasers, initially fairly low power, but we over the years rose to thousands of watts of power within a single mode fiber, 9 micron fiber. And now it's pretty much become the way that metal is cut or welded or marked. It's now the dominant form of laser technology. Along that journey, I mean, we were VC backed. California VCs was the original SPI lasers. Then we did a bit of flotation on AIM, then it was sort of pension funds, which a lot of maintenance on the AIM market, a lot of overhead for the CEO and the executive team. But in the end, a trade sale to a company called Trump, which is one of the biggest machine tool companies in the world, but obviously also one of the biggest laser companies in the world. Yeah. Very, very good. It was very interesting dynamics there, being bought by a German company who are, as typical German companies, although they were 3 billion in revenue, they were privately owned with no debt. What a great company, and what a great attitude to manufacturing and to looking at how things should be done, and taking a long-term view. So it was an education in its own right, sort of one of the aspects of it, we were struggling at SPI Lasers to make a profit, but we simply couldn't turn over enough product without adding more staff. We hadn't really cracked that cycle of the overheads kept growing in proportion to the output. We never seemed to be finding the break even though we were going up in turnover by tens of millions. We were never finding the break even point.
Right. Yeah.
The acquisition by Trump Laser, they sent a team across called a Synchro team, who showed us how to get 3 times the output from the same number of staff, and that was, an education, which obviously broke the cycle, and we managed then to become profitable.
Wow.
But we were seen as enabling to their machine set. They obviously had lasers, but they had lamp-based lasers, and they wanted this new fiber laser technology because it was seen to be the future.
Yeah.
So we were seen to be an enabling technology for them. And they were selling their machine tools for 400,000 to 500,000 euros for a cutting machine.
Yeah.
So putting an advanced laser on it would help that sale process, and therefore be highly valuable to them as a company.
And it's actually, you say commonplace. I mean, it really is. And in the EV industry in particular, laser welding and joining is used in a lot of different places, and actually has enabled things. So things like hairpin motors probably wouldn't really be possible without the ability to do very clean laser welds, large format battery packs. So laser welding of tabs to cells, very common.
Exactly. Dissimilar metal welding was not an easy task. If you wanted to join sort of copper and aluminium or other sort of more exotic materials, it was hard using traditional laser technology. But the sort of beam, the Gaussian distribution beam coming out of a single mode fiber of a fiber laser led to much higher intensities. And also you could play around with waveforms to create effects. Yeah. So it was, as you say, an enabling. One of the early things we did actually was putting the Apple logo and the wording onto the iPhone. That was our,
right. Okay.
This was all done by Foxconn, and the biggest orders we had in the early days was we developed a particular way of marking using our fiber laser that was very attractive. I remember I pitched it to Johnny Ives in Apple, and we spent about a year. We put our own development center into California to simply develop the way things could be marked, with the idea that we would attract Apple. That was always a key target.
Yeah.
And in the end, we got those orders, and then that helped us to build our Chinese business, because all of that activity actually takes place in China. Yeah. In Foxconn factories that typically have 300,000 to 400,000 staff. It's a different world out there, and we got us into a company called Hans Laser, now one of the biggest laser companies in China. But when we started dealing with them, that wasn't the case. And they were putting the marking machines initially, but then it went on to welding machines as well. Yeah. Into the Foxconn factories.
It does. Just sort of circling back a little bit, it strikes me like a lot of people, and I know a lot. I talk to a lot of younger people, and actually would be worried about doing a physics degree because it's quite, they see it as almost being limiting. And to a certain extent, I might have thought that as well. Maybe engineering a bit more, if you're that way inclined, mech eng, sort of more application based. But your career at this point is a real example of actually, what an amazing platform to go from that founding in physics had become.
I totally agree. And I think if you were a mechanical engineer, then if you're in a meeting, people tend to know what you know. You're a mechanical engineer, therefore you must know these things. Yeah. I typically obviously spend most of my time selling to heads of engineering, chief scientific officers, CTOs, etc., the technology of whatever company I'm at. But what they don't quite know is what I might know. Because as a physicist, you know quite a lot fundamentally. You may not know things in the way that an engineer would. I can't construct something necessarily, but I can understand a technical concept. Yeah. And it even does roll over into sitting, in more recent times, I'm sitting with chemists because I'm now in the battery domain, electrochemists. But they also respect what a physicist might know about a situation. If you give a physicist the fundamentals of something, they get a good grasp of that. Yeah. They may get lost after that in the detail because it's not, they haven't specialized. But even within physics, there was many modules. There was semiconductor modules and other quantum physics, etc. So you were able to study 5 or 6, 7 different modules of physics, which took a breadth of knowledge. And I've always found that people have had a great respect. And I would actually really encourage people to see physics as a great business degree because it's just a foundation. And after that, in effect, you're doing whatever you do for your career.
Yeah.
But actually, you've just got this very solid foundation.
Yeah, I always tease my economist or accountancy friends, if you go and study economics or accountancy, you're going to be an accountant. You can't go and be a physicist if you study accountancy. Whereas if you study physics,
the reverse works. You could be that accountant if you chose to be so. Yeah.
Yeah. So you then made the sort of jump out of laser technology into solid state batteries.
No, there was one in between. And this was, I realized along the way that I liked early phase companies. I liked helping a company from its early days through to a particular point. But I had worked in large corporations. I said British Insulated Calendar Cable, BACC, was a multi-billion-dollar organization. And of course, that comes with a certain overhead in politics or structure or formality, but also an overhead in you get a very narrow focus because there are many people like you and your remit is narrowed down in a large organization. In a small organization, as in the SPI lasers, you initially you do everything. You have to get involved in every aspect of that company because the company might only have 10, 20, 30 people as you're growing it. And that's fun. It's worrying, but you don't always know you're going to get paid next month, but it's fun. So I realized that was what I like to do. But I remember also listening, and this was I had to drive to work, and I was listening thinking, the UK industrial sector is rather small. I think it's 10 to 15% of the UK economy is manufacturing. The other bit, there's a farming element and then there's a retail element, but there's also this consultancy element or services element, which is the larger element of the UK economy. And I did wonder, I guess I was coming to my 50s thinking, I wonder if my skills are transferable. And I've always had a thing about transferable skills. If you believe you have transferable skills, you're never going to be worried about being out of work. Because you can always apply those skills to another sector. Yeah. And I'd always worked in manufactured product right from the beginning, from the AVO days. We'd always made a widget and we'd sold a widget. Typically, we'd sold that widget overseas. But I did wonder whether I could sell a service.
Okay, yeah.
So it happened that the ex-CEO of CFAM, who I still mountain bike with, still even to this day, I go mountain biking with him, we're still friends. He was also chairman of a semiconductor design company called Sondrel. And he recommended that they were seeking a VP of sales and marketing. And he was saying, would you like to apply? So he didn't give me the job. It was a proper application. But it ended up, they've got about 200 design engineers designing sort of the physical layout. It's called the sort of verification and layout of a chip. Yeah. So this would typically be an advanced node, the time 9 nanometers, not microns. Yeah. 9 nanometer design. Yeah. And it could take 100 to 200 people to do the actual design and verification and physical layout of a chip like that, and it can take 2 to 3 years. Yeah. To do that. And this company, Sondrel, probably definitely foremost in the UK, quite unique actually, deployed that level of resource. So often the customers were in Israel. Yeah. Very seldom were they in the UK. UK doesn't tend to design that level of chip, but customers could be in California and often they're in Israel. Yeah. And they were either they had a team, but the team wasn't of a large enough size, and they wanted to start their next chip, or they had no team and they were virtual and they wanted to develop that chip. Yeah. And so they would call Sondrel in, and effectively we were renting out, using services. We were renting out our skills as a engineering team. I did notice even in the 5 years I was there were fewer UK-based engineers. Our headquarters had fewer and fewer UK-based engineers, so therefore we had to seek engineers overseas. Initially, we took over a design center in Morocco that had been people at ST Microelectronics had been released, and we took over that design team. And then we went on and did the same in India. And we also always had a design team in China, in Xi'an, in China. So
that's a good spread.
It's a good spread. It did allow for kind of round the clock working, which, in terms of follow the sun, they call it. Where you can get sort of design teams handing across. So you're using more of the 24-hour clock. But it also meant we could connect with the semiconductor industries in China, in Europe. etc. So it was fascinating. For me, moving into selling a service, selling people's time and skills, and also for me to understand semiconductors. I had, as part of my physics, studied semiconductors, but this was really understanding. Me having meetings with TSMC, having meetings with Intel and Infineon and the large Marvell and all of the big chip companies, seeing, because they're in everything. Every single product we look at has got a chip in it. Even in the audio industry, again, products and their mixed signal products in everything. So, just to really understand how things came about, how products came about from that perspective. Probably over my career, every product I've worked in had a chip, but I just ignored it because, hey, it wasn't my area. My area was different. But now this was my area. So it was 5 years, and again, learning a lot. Again, I actually realized that two things. This was a much more mature company again. So it hadn't got that early stage feel to it. And an opportunity came up very close to home, actually. The laser thing, the semiconductor thing had been an hour or so's drive each way to get to the office. And an opportunity came up with Ilika, who are literally 10 minutes around the corner from where I live, who are early stage, and was going to really clearly use some of the skills that I'd already developed in early stage companies and in technology companies. And they were at a very interesting point themselves. They were at a point of pivot. They weren't at that time necessarily seen as a solid state battery company.
Oh, really?
Because they span out of Southampton University, I think in 2004, and their idea was materials science. They were helping large companies with using co-evaporation and sputtering techniques to do layers of material deposition onto wafers, and then study those materials and the compositions, and really trying to create intellectual property of material science for large organizations. And they had at some point in their history, they had an ARM guy as their chairman, and so IP was fundamental to them. And so that was really, for 12 or so years of the life of Ilika, that was their business. It effectively, you might call it a very high-end consultancy. They were working for, could be large OEMs. They did work for Toyota in, I think that was as early as about 2008, 2010. They created intellectual property in battery electrolytes for Toyota. So they had the capability to do that, but that wasn't their main mission. Their main mission was to simply help companies to develop new materials and understand the properties of those materials. So they had a rig both at the university and at a campus, which was a university industrial campus. That's where the spin-outs go. But along that, they also had developed a thin film demonstrator, sort of generation 1 micro battery, about 1 centimeter by 1 centimeter.
Right.
And this was to demonstrate that you could make a battery, a solid state battery, a purely solid state battery, out of depositions onto a glass wafer. But it hadn't necessarily been seen at that time as that was where the business would totally go. Although it was definitely evolving in that direction quite strongly. And then they had, I think just at the point I was joining, they'd applied for grants from the Faraday Battery Challenge under Innovate UK, where they said, well, we've got this thin film battery technology. Potentially we could upscale it to inks and a larger industrial scale, and it might then be applicable to electric vehicles. So they had 3 projects awarded to them with 3 OEMs. 3 car OEMs, and each of those looked into slightly different aspects, but overall the idea was to create a pouch cell for the electric vehicle sector. I think they got about 6 million in funding.
Wow.
Probably part of that was the money Ilika put in itself, but there was funding and those 3 projects, and that allowed them to create a dedicated facility. And now for the first time, the Ilika that we see today is emerging. They now create a totally dedicated team and a totally dedicated facility to the study of electric vehicle pouch cells. And that was about 2 to 3 years of activity, and brings us more in line with where we are today, I guess. But the company also decided at the time to also pursue and industrialize its micro batteries. So these are depositions, thin film depositions onto a glass wafer, 6-inch glass wafer. And these would be used in particularly implants into the medical sector. So here, the idea of making a battery on a millimeter scale. Now, if you look at medical devices at the moment that go inside the body, it could be a heart pacemaker, or it could be a impulse generator for nerve stimulation. They're typically a large battery with some small electronics, because the battery needs to last a number of years.
Yep.
I think 85% of the batteries in the body are primary batteries. And so there's only about 2 or 3 places in your body that you can place a large battery. It's in the heart space and in the buttocks. And so it's very a big operation to actually get a battery get a medical device into your body. Tens of thousands of dollars. The device itself might only cost $2,000, $3,000, $4,000, but getting it into the body is a factor of 10 of that. And so the idea is this could be a market ready for disruption. What if you could make a much smaller device that you could charge much more quickly? Because even the 15% of medical implants that are rechargeable batteries, you tend to go to your doctor's surgery to get them recharged, because they can take 1 to 2 hours, as you know, C rate of C over 2, or maybe even at best a C rate of 1. So you can't really trust somebody at home. They might not sit still enough, they might not do it properly. So you go to your doctors, you sit there for a couple of hours, you recharge the battery, and that's how it's done. So the thesis here is, if you could charge in 10 to 15 minutes using an inductive thing that you're holding to your body, if you can plant a thing in a much nearer to the skin, because it's actually a much smaller device, you could really change the way people perceive medical devices. And this was helped by the fact that there's been a big crisis in America, the opioid crisis, where people generally do have pain. I mean, maybe the feeling is, they're all addicted to drugs, we should take them off the drugs. No, they do have pain as well. So you can't just say, stop taking the drugs. So there's been a big study, a lot of money and investment in how do you address this subject. And one of the things is like a TENS machine. Many people will have, when their partner was having a baby years ago, they had a pain blocker, which is a device they wore around the waist that they turned it up and it blocked the pain. Well, we're talking about things the size of a pill that do the same, that block the pain.
Oh, wow, okay.
And then there's been many studies into the vagus nerve, for example. You've got these arterial nerves inside your body. And these are, you can work on epilepsy, you can work on dementia, you can work on even eating disorders. They're all impacted by tiny impulses of energy imparted to the arterial nerves in the body, the vagus nerve being a classic. Whereas lower back pain, another real use of why people might be on opioids, can be spinal cord stimulation. So there's a whole new branch of medicine, bioelectronics, where people are looking at what if we stimulate various nerves in the body, what effects will we get? But one of the requirements of that is to make these devices a lot smaller, a lot cheaper to implant, a lot less invasive, and therefore you're going to need a next generation of batteries. So ilika's decided to focus on that for its it's called the Stereax side of its business, but it focuses on that.
Because you sort of, am I right, you've kind of split the company into 2 divisions?
It's one company, it's 2, we haven't really formalized it in business units, but actually they're totally different sites on totally different teams. So it may as well be business units.
2 divisions,
It's, and they're doing quite different things, because they're both solid state, both fully solid state. But I say one of them is making thin film depositions onto a glass wafer. It's just a co-evaporation techniques and sputtering techniques, very similar to semiconductor. We had hopes that we were simply going to use semiconductor resources that the UK already had, 6-inch fabs that were in the UK. But because of our lithium, the CMOS factories were quite clearly not very keen on that. It might have destroyed their yield, and they've got a high volume process. So we realized that we were probably going to have to set up our own fab. And we did a money raise where, I forgot to mention, but ilika's on the AIM market. It's a listed company. And in 2020, I think actually just as lockdown was happening, we were doing a money raise purely in relation to the Stereax side of our business, so that we could afford to build a fab and also fund the development through to industrialization, which is where we are now. And I think the money raise was about £15 million. And we're now, year 2022, we're now industrializing, bringing our Generation 2 product to market. But the key thing is bringing it to market on industrial equipment, because it had been developed on university equipment. And there's a big difference between the two.
Yes.
So we've now bought a set of industrial equipment, got multi-thousand wafer capacity, and we're now transferring the technology that we developed at the university onto that equipment. And then later on in the year, the product will come out. But it will still take some time to get into the body because FDA compliance. We're speaking to companies who have to go through very strict compliance and test. So it'll still be 2, 3, 4 years. But areas that I think might come first might be smart orthopedics, for example, where people are getting knee and hip implants, and a percentage of those don't take. But actually, if you leave it too late before you find that they don't take, the cost of extraction is extraordinarily high.
Yeah.
Whereas if you can understand early that the bone growth isn't happening, there's a pressure or a hot spot, you can intervene, and it's a lot cheaper operation.
Oh, wow,
so what they want is a Bluetooth-enabled sensing device inside the knee or hip implant
cool.
that sends information to your phone, that then sends information to your doctor. Your doctor phones you up and says, you better come in. And this is actually much quicker to market because this is not a life or death type activity.
I actually wait for. I just found out I've got a knackered hip actually.
So
I'll wait until
having a smart device. It's called smart orthopedics, and it's going to be the next generation of orthopedic devices.
That makes a lot of sense. Yeah. So the micro battery side of things, you clearly said it's a material deposition process onto a wafer. So am I right? Because there's quite this generic term solid state batteries, but there's quite a few sort of subclasses of solid state. So would that be what people commonly refer to as a ceramic solid state battery, where you've got that kind of structure? Is that?
Well, even on the larger scale, they become ceramics. You sinter them, and they become ceramic oxide materials in our case. So I think probably the small ones, the word thin film tends to be what gets used, and the fact it's a sort of evaporated material onto a substrate, but it doesn't scale, and that's the thing. People often say, "Well, is that how you make have you simply scaled that up to make the larger format batteries?" No, it's a very expensive. There's about 200 production steps in this tiny thin film battery. We may, because we also stack the batteries, we may only get 100 batteries off a 6-inch wafer. Right. And these batteries might be giving 1 milliamp hour of capacity.
So when you say stack them, so presumably you got your wafer, you're building it material, then you're dicing that into little squares, and then you're stacking the squares up. Is that right?
Yes.
Okay. Yeah. Right. Okay.
So you thin them down to allow, because the substrate is parasitical. It's not part of the battery. It's purely a carrier. So a wafer might be 1.5 to 2 millimeters thick to begin with, but we thin them down as thin as possible, really. We're currently about 90 microns, but we're hoping to go a lot thinner than that. And then we stack them so that increases the energy density. You're not stacking parasitical materials on top of each other.
Got it, yeah.
But yes, the stacking is a very important thing to get enough energy storage. But even so, we're still talking about now sub 1 milliamp hour capacity, and even in the future 1 to 2 milliamp hours capacity. Yeah. So we're relying on electronics being a lot more energy efficient, which it is. Good news, that is true. And also these batteries have a feature where they can hit a C rate of 10 or even a peak of 20. So a 1 milliamp hour battery could actually power easily a Bluetooth device. Even a LoRa device would be no problem at all. Okay. Because these devices, like a Bluetooth, is milliseconds to transmit on a radio, but might need 2 to 3 milliamps to do so. But a sort of microamp hour solid state battery can easily do that. So in some ways, they're like a hybrid between a battery and a capacitor, a super cap and a battery combined in many ways.
That's interesting, because one of the things that I often sort of think about with solid state batteries is actually they're not very good at high discharge conditions, but for the micro batteries, then obviously that's not.
These are exciting, and we don't know yet and we'll talk in a minute about the electric vehicle batteries, what the potential might be for C rate there. Yeah. But actually, certainly on the thin film side, it's a very good outcome. It's I say that makes it more of a hybrid component, which is I think it's going to be interesting. People are going to adopt it in areas that we can't yet imagine. But we're aiming typically, and the same story I guess is going to be true on the pouch cell side, is when you've got limited capacity of something which initially would be quite expensive to make, you look at who might appreciate that. Yeah. And certainly implants in the body The volumes initially will be quite low. The affordability will be quite high.
Yeah.
And therefore, it's a good initial market for us to go for. So that's our Stereax side. And then, as I said, the UK grant, Innovate UK, Faraday Battery Challenge, funded this separate activity. We are probably one of the foremost companies in the UK looking at pouch cell related solid state batteries. And this activity is now getting quite exciting too. We did a money raise in 2021, so only last year.
Yeah.
This was about £25 million money raise. And this was again to take this particular technology forward through industrial stages. There's obviously development of the technology itself. There's still at least 3 years of development of the technology. But there's also, it needs to be scaled to show that it can be manufactured at reasonable points of scale, and you can't just jump to gigascale.
Yeah.
So we start off, we're increasing our current facility, the one that the Innovate funding got us, which pretty much has got maybe sort of 1 kilowatt hour capacity per week.
Yeah.
Really lab scale. We want to get to early megawatt hour capacity, and we're going to use the funding that we've recently got to get us to the low megawatt hour capacity per year. Then there'll be a subsequent point of scale taking us to hundreds of megawatt hour capacity. And that will be the evidence that we believe will allow gigafactories to say, well, yes, it can be done. You need these points of scale in between because, as we know, I mean, I'm up in the Newcastle area, and yesterday I certainly made a point of visiting the Blythe facility.
Yeah.
It cost billions to put together a gigafactory.
Yeah.
So they need to know the technology is working and scalable.
And one of the challenges that often we talk about, so a conventional battery, and it sort of doesn't matter if it's a pouch cell or a cylindrical cell or whatever, but the production process is what we call, or people talk about, as reel to reel. Mm-hmm. So you've got these really super high speed, enormous reels of material, and the whole thing comes together. So you're bringing the anode, cathode separators together at very, very high speed into cylindrical cells or onto pouches, forming it into the right size, and then obviously filling it with an electrolyte, which is this liquid, and sealing it, and then you goes through a conventional battery. It goes through this sort of magic voodoo process where they bring it to life and condition it to get it functioning properly as a battery. So that it always sort of, the first time I saw a plant making things like that, it looked like the sort of like almost like a newsreel, sort of just lots and lots of material flying around, super high speed for the huge volume. But then sort of transferring that to a solid state process and working out how the same, because it is scale on another level, the conventional battery plant. So how that solid state process will transfer to that sort of scaled up process, it's quite hard to envisage. So it'd be interesting to know what your steps look like in terms of being able to build these larger format batteries. It's presumably you're not depositing materials on a wafer anymore. You must have some.
No, I say the wafer thing is a completely separate thing. No, I mean at our Goliath factory, the Goliath is the sort of brand name that we call our pouch cells. Okay. At lab scale, in terms of as it was created for the Faraday Battery Challenge, it was silk screen. So the actual depositions of the materials were that silk screening process. Okay. We needed to be sure that we could then roll to roll, which is what you're saying is these fast newsprint style processes. Yeah. We actually right in the middle of the COVID lockdown when we determined that we needed to know this. And we tried to find sort of UK facilities that we could work with, but in the end, we ended up working with the Jülich Institute or on a machine in a German technical institute near Aachen, where we did trials to prove to ourselves and others that we could do roll to roll, because it was a critical thing. Unless you can do roll to roll, you're not going to produce things in high volume. Yeah. So that was very encouraging, which allowed us now in this intermediate scale up, the first scale up, to now start with, in the next few weeks, actually going to be buying or placing the orders for the roll to roll machinery that will operate at that level. This isn't the giga level by any means, but I say at that level, they'll be appropriate leveled. But then it's fascinating that you are right. The critical thing here is how much of the equipment in an existing gigafactory might not be relevant to a solid state. Because if hundreds of millions, if not billions, have been invested, you really don't want to say to that gigafactory, just forget that. We're doing it this way.
Put it in the car park, guys.
You have to have as many of the processes recognisable to these people. So again, very supportive from the UK government. We've worked with the ATF, Automotive Transformation Fund, and we've worked with a company called Comau, which actually maybe not so many people might have heard of, but actually they're part of the Fiat Group, who are now part of Stellantis. So we've been working with them for a year on exactly this question of what is the machine set that will be required to mass produce our version of a solid state battery. And they've drawn up the facility as it will look at, I think, about sort of 200 megawatt hour scale, so the intermediate scale. And they've drawn up each machine stage, what it will be, the size it needs to be, the throughput speeds it needs to have. This is a white paper study, but it's been a very fascinating study. They've been communicating with the machine builders as well, and really looking at which of the processes are recognizable to people today in the lithium-ion battery market, which might be just a customization of an existing piece of machinery, and which might need to be unique. One of the unique things is sintering. There is no sintering step in a lithium-ion battery, but there is a sintering step in our battery. And therefore, what machinery required? I mean, tunnel ovens are well-known ways of sintering things, but we're also studying more novel ways because we're trying to eliminate any batch processes. If you've got a high volume, as you talked about, roll-to-roll newsprint type machine that you suddenly abruptly put the brakes on and move into a batch process. Well, there is in a lithium-ion battery a batch process. It's called formation and aging. And actually, because of it being a batch process, it takes up a third of the entire capital, a third of the electricity, and a third of the physical space. You could, in a gigafactory, have 40 to 50 million pounds worth of WIP sitting in this formation and aging stage, which can take 25 or so days.
The magic voodoo part where they bring it to life.
Where they bring it to life. So now, actually, we're hoping our technology will have a much reduced stage like that, but even so, we really don't want batch stages if at all possible. So this is what we've been working with Comau on, and then we're also doing a study. We were part of, I don't think it's how I met you yourself, Ryan, on TDAP, which is the Advanced Propulsion Centre. Run a series of every year actually. I think they run it. About 10 companies get awarded to operate on their business strategy, and that's how we met. You were talking at an event, and I met you there. But under that, the first year is they work on your business strategy, and a fantastic job we've been having working on that. In the second year of that program, you're allowed to work on a technical validation point. We've just passed last week, passed our second phase in terms of we're now into that second phase, and we're working on formation and aging. So we described to TDAP, TDAP by the way is Technical Developers Program. But we described to them that we wanted to study this formation and aging stage to see if our version of it was a lot shorter and cheaper to run, because that would be a big selling point to gigafactories. So we're now, between now and October, doing many experiments in our factory in a very structured way to look at the differences between lithium-ion battery formation and aging and our solid-state battery formation and aging. So that's it's going to be quite exciting to understand that result. But anyway, we're also, and you've touched on such an important issue. We get QuantumScape leading the way in terms of marketing where they are technically. But also, as you'll see, getting hit quite hard because people are very worried about industrialization. So it's great to put good data on the table. But are you sure the thing you're putting on the table is a thing that you can industrialize? And I know in recent weeks, QuantumScape have come under pressure because a lot of the data is relating to a single layer coupon size object. And the question is, does that really translate to a 50 layer larger object? And until you show us that it does, we can't really fully understand the results you're showing us. But even if you do show us it does, are you able to mass produce this thing? And so maybe a slight difference of what ilika have been trying to do is work on the mass production completely alongside the development, so that we don't take steps in development that won't allow for mass production. Because otherwise you can end up with a technically very interesting object, which is not mass producible. And we're very keen not to do that. So we're also applying for next generations of government funding where we're going to keep on studying this and also keep on looking at the mass producibility of what we're doing. So we're really trying to do this in parallel. We took a guy called Brendan McCarthy, who put the Battery Industrialization Centre together. He was the operational director at the BIC.
Okay,
Before that, he had 40 years at BMW as plant manager around the world.
Right.
But we took him out of retirement and offered him a role, and he's now our operational director at ilika. And we've also just hired a new NPD director, new product development director called Robin Bell. And so we're really making sure that every step we take is taken because it is industrializable.
Right.
If there is such a word as that.
And so sort of, if you can, in simple terms, for me, the process of making so we're talking about thicker films now. So
yes, yeah, hundreds of microns. Yeah.
Making what does it look like? What is this sort of 50-layer solid-state battery? What are you bringing together? How do you bring them together? How do you make a solid-state battery like that?
Well, it's a much thicker, I say, compared to the thin film object, but it's a much thicker. But when I say much thicker, it's still less than 200 microns thick. But the cathode, is of that sort of order.
Yeah.
The idea is to make the electrolyte as thin as possible. So that's a different thing. You're trying to make as thin while still having a barrier.
Okay.
Because you're still wanting each layer to be as thin as possible in an overall sense. So you want to pack as much lithium into the cathode as possible. You want the separator electrolytes to be as thin as possible. And then, of course, you get these different flavors that everybody is working on. QuantumScape trying to work on an anodeless design, a design that has no anode, simply forms the anode each cycle and then reforms. You're looking at companies with lithium metal, where they're thinking a lithium metal foil will be their anode. And then ilika is of the silicon camp. We're saying that our anode will be silicon. And our thin film batteries have got a silicon anode as well, so we've got a few more years of experience in that. But again, each layer of battery, maybe back to the Stereax, as I mentioned, isn't that thick. It's just that you want 30 to 40 of them to get up to the multi-amp hour pouch cell. So you're looking at an object, or we're looking at an object, which will be about 100 by 300, which is a size that the automotive industry quite likes, at about 10 millimeters thick. But that 10 millimeters will be layer upon layer, with obviously separation between them.
Yeah. And you mentioned electrolyte. So is the electrolyte a solid or semi-solid type?
Fully solid.
Fully solid.
Again, looking around the world, and there's no right and wrong answer to this, because time to market is important, revenue is important. The Chinese tend to have gone for semi-solid. You've got Prologium and Welion and a few others, and therefore they've got product coming out. And I think there's a recent release with Daimler about that. So they will come to market first. They tend to be semi-solid products, more polymer-based products. And then you've got the pure solid-state people who will be coming to market later. And in those, you've got sulfides, quite a few, half the companies, Solid Power maybe being an example, but about half of the companies have chosen that their electrolyte material should be a sulfide material, and half have chosen an oxide material. And there's merits for both. The sulfides can give you a more energy-rich product.
Right.
So you're more likely to get a higher watt-hours per kilogram from that product. However, the rate of learning that the sulfide needs to have to cost in is going to be a longer journey. We're in contact with the producers in China, typically. The producers are in China of these products, or of these electrolyte materials. And they're telling us about what you could buy at tonnage costs now for the oxide-based electrolytes, and what you could pay tonnage levels for the sulfide-based materials. And there's a vast difference between the two. And the learning rate will be longer anyway on the sulfides. So it does lend itself to the fact that sulfide-based solid-state batteries might come to market somewhat after the oxide-based ones. But also, in our view, the sulfide has issues of handling. We always intended to manufacture in the UK, and it's quite a material to handle, the sulfide-based. It has side reactions and reactions with the atmosphere. You'd have to keep your factory at a very, very low dew point. And therefore it's a much more expensive environment to be working in. The outcomes can be worse in terms of the side reactions can be worse.
Yeah.
So we just, actually we did some work on it, but in the early days, but we decided oxide for us, if we're likely to manufacture in the UK, we'd like materials that the UK people would like to work with, and environments that are better working environments. So we're heading down the oxide route ourselves.
I remember having in a past life some quite big problems with sulfur migration into some electronic components, which basically ruined them. So just like the sort of life cycle side of it, it was a particular component was giving off sulfur, and that was finding its way into. I remember what it was now. It was basically a shunt resistor on something where the value of that resistor was being substantially altered by the absorption of sulfur over quite a long period of time. So imagine those sort of degradation mechanisms inside a battery cell would be quite critical, actually.
Well, we're looking really at the raw materials coming into a factory being handled within that factory. There could be some side reactions with moisture that could cause acidic sort of outcomes. I think quite rightly the battery industry would say that once it's contained in a module in a pack, there's no real discussion about safety there, because actually people are driving around in cars full of petrol and fuel. So that's not exactly safe either. And yet it's been made safe by the quality of the containment. So the OEM or the battery pack provider will make whatever it is safe. If they didn't, they wouldn't be in business and they wouldn't be allowed to put it on the market. So they don't like to have that conversation about it. However, in transportation and storage, before it goes on, logistically, if you had to make batteries that you then had to ship into a warehouse and put onto a ship, etc. Again, it's not yet necessarily fully been made safe. It maybe is at cell level by this point, not yet in a module or a pack. You'd want it to be a safer outcome, and oxide is a safer outcome. But I say once these things, whichever chemistry set gets used, once it goes into a car, by definition, it will have been made safe and contained.
In a conventional battery, a lot of the issues with safety come around from the electrolyte. Gets to a point where it starts to break down, and then kind of exotherms, and when it
the thermal runaway effect.
Very difficult with a conventional liquid electrolyte, and a lot to do with the solvents that are used in those to make them liquids in the first place. Is that issue, or that sort of issue, completely gone with a solid state? Or
yes, I'm not so sure it's on it probably is on our LinkedIn page. If you go to ilika, we've got a nice picture of somebody using a pair of scissors to cut a cell in half while the cell still works. So the cell is powering something, and then we just cut it in half and it's still powering something. Nobody blew up, nobody died in that experiment. That's a nice way of showing safety. I think the same person also rolls the cell up into a tight little roll just to show flexibility of the roll to roll. Yes, there's and then we've got, haven't yet put them on the website, but we've heated the whole thing up to 85 degrees, which a normal cell really wouldn't like. Normally you're trying to keep cells at 40 to 50 degrees or even less than that. But we've taken the cell up to 85 degrees to show. Now we'll keep on pushing that to see where that point of breakdown might be, but there won't be the thermal runaway because, as we know from our Stereax batteries, on our Stereax batteries, by the way, we can take them to 150. The reason we're stopping at 85 so far on the Goliath battery is the pouch. We haven't designed a pouch, which goes to high temperature. But we need to do some studies on what happens to the materials inside the pouch. But it'd be helpful to do that when we've actually got a pouch that we know survives. So I think it will be a very interesting area of study to see how these things work at high temperature.
And I imagine, so just sort of my take would be the thin film cells, because you're depositing thin films, actually things like differential thermal expansion and stuff become insignificant problems because you've got very small layer thicknesses, so actually it can all kind of comply together. When you go up into a larger format cell, I sort of understood, again, an issue with solid state was essentially sort of stress between the layers and cracking and issues like that happening. Is that still a problem, or is that something that you've managed to solve somehow, like that? The sort of, and particularly you're talking about being able to run to higher temperatures, which would be really useful in a battery pack, actually, to be able to operate even slightly higher temperatures than a current pack. Could get away from. There's a huge amount of equipment needed on an EV to keep the pack it at its sweet spot, subcooling and chilling and all this sort of stuff. So absolutely could see a slight increase even in operating temperature would be really appreciated by the industry. But then how are you managing the thermals inside the pack then, and sort of those differential expansions and things between those still thin but thicker sheets of material? How does that play out?
Well, for us, we're still ourselves at the single layer stage, and we now, over the next 1 to 2 years, are going to start stacking. But you're absolutely right. If we're particularly using a silicon anode, we need to understand the issues of expansion in the anode. That will be an issue. People using sort of carbon nanotubes and looking at the morphology of the silicon, so that it's how it compresses and where it compresses, and does it compress down into the battery or does it go upwards? But the results will only come from actually doing. We can model it and we can simulate it. But the real results only come from actually doing it, and we're not yet at that stage. And the question we always often get asked is, what level of compression do you want to keep the whole thing at in the first place? Now, so far, the results we're showing are with an uncompressed battery. We don't yet compress our battery. We don't have a need so far. But that's not to say that it won't. When we start stacking 10, 15, 20 layers, there will be a lot to learn about expansion and compression. So this is what would be happening over the next 2 years of our NPD program, our new product development program, is to get to these points and then to understand them and then work out whether we need to work around them or whether we don't. And that's a key thing.
So people might not, people in the battery industry would know this, but people outside the battery industry might not realize, but a pouch cell, which is sort of a semi-flexible thing, when you build that into a module, actually you create the module in such a way that it applies a pressure to the surfaces of the cell. So this is a conventional battery, so it's already part of battery pack design today, is this sort of pressure, and it's quite a key factor in the design of the pack, being able to manage a consistent pressure across a conventional battery cell as it expands and contracts in operation with temperature and state of charge and stuff like that. So it's actually, it looks quite simple, a battery module, but actually when you get into it, maintaining that on a conventional battery system is really difficult in practice. Part of the reason why some people prefer cylindrical cells is it's built into the cell, then you don't have to worry about it. But if you could get away from that kind of thing, that would be a huge result.
Which is there's next generation, as I said, of grant funding happening under APC. This is APC 20, but we have put a collaboration team together with 3 tier ones and an OEM. A lot of it is to look at this. We've got sort of people involved in cooling systems, people involved in battery pack development, and that's what their aspect will be, is take cells from us and test out these outcomes and see. The word in pack development is gravimetric cell to pack ratio, which effectively means how much of the battery or how much of the chemistry in relation to the overall battery system. And I think BYD sort of rocked the world about a year or two ago by getting they basically got rid of modules and went straight from cell to pack, and ended up with late 80%, 85, 90% gravimetric cell to pack ratio. And what destroys that is safety packaging, thermal packaging, as you say, to keep the cells at the right temperature, to keep them doing thermal runaway. All of these are parasitical. And they basically reduce that gravimetric cell to pack ratio. And people are fighting hard at cell level to get a certain number of watt hours per kilogram to throw it all the way at pack level. So as this new trend towards LFP has shown us, is that if you have something that's more inherently safe, you may lose it at cell level, but gain it back at pack level. And that's effectively what BYD did. Is they sort of showed this sort of, it's not as important as people thought to get the optimum or ultimate cell. It's more important to worry about what's happening at the pack. Yeah.
As ever in life, the sort of system level thinking being really critical. Yeah. Fantastic. So just then to sort of bring us to a close, that's been absolutely fascinating. I've learned a lot about what you guys are doing and the industry in general. What's coming for you? What are you excited about in the next year or two that's coming down the line?
Well, it's a fascinating job. Back to why would a physicist want to go into this business development, techie product type job? But on the one hand, 2 weeks ago, I was at the Neurological Society of America conference speaking to surgeons about implants into the body.
Yeah.
And actually, in about 2 months' time, I'll be at a smart orthopedics show. And then after that, I'll be at smart contact lenses, where we're looking at virtual reality, artificial reality, putting batteries into contact lenses.
Oh, wow.
In the last week, I've spoken to Meta, I've spoken to Apple, I've spoken to Samsung. So you're actually working with companies who are going to invent the future, and that's a fascinating area of business to be in.
Yeah.
So that's on the micro battery side. On the large format batteries, we've got roll our sleeves up, 2 hard years of product development to do, but running completely alongside it, a manufacturing scale up. We're going to try and run both of them in parallel, so there won't be many quiet moments. It's going to be a busy time, but it is nice working in a sector where you're on topic.
Yeah.
I mean, you couldn't get more in the press about going green and getting rid of internal combustion engines, etc. So you're always working in an area where actually, weirdly, for once, often when you used to go to a party and people said, "What do you do?" "I work in sales," they used to walk away. It's like, oh my God, he's a salesman. But actually, for once in my life, I'm a salesman in the right place at the right time.
It's when the people kind of understand.
Yeah, well, they want to know. Yeah. They do. Oh, so is my car going to have more range, or can I charge it faster? And these are topics that a lot of people I know are actually waiting for. They're not buying the battery car because there is a slight, more than a slight issue. That not that many charge points is one of the issues, but they are worried about range, and they'll only really be comfortable about range when it begins to come in line with their petrol tank.
Yeah.
They understand their petrol tank is going to get them 200 to 300 miles.
Yeah.
This idea that my car might only get me 150, it's a worry.
Yeah. I can see. There's so much going on for ilika, and absolutely fantastic to see this sort of stuff in the UK. Even, I think If I'd have thought about where the center of gravity was on solid state batteries and who was a more advanced player on this until I met you, actually, I wouldn't have thought that being in the UK. So it is fantastic to see. Actually, there's a few things on the story. You're a university spin out effectively that's now absolutely going gangbusters and a real success story in terms of raising money on the public markets and stuff. But then actually at a really advanced stage, kind of leading the way on solid state battery developments globally, when there's a lot of noise from other parts of the world, and it seems like you guys have just been quietly getting on with this. And
it is, and that's some companies like QuantumScape with their IPO maybe had to make the noise. That's part of it, and having got such a high price for their IPO, maybe felt obliged to keep on making that noise because they've got a lot of investors to keep informed.
Yeah.
It is really dependent on the company. There's an awful lot happening actually in existing battery companies where you're hearing nothing about it because there's no need for them to tell people.
Yeah.
Or within Toyota, we know Toyota are working on solid state batteries, but actually they're Toyota, so there's no need to tell people what's going on.
Yeah.
So I think the noise is coming from a relatively small number of companies compared to the number of companies that are working on things.
Oh, right.
But
okay.
You do have to be careful to, if you do make the noise, you do stick your head above the parapet. We've got existing very supportive shareholders. The UK government, via its funds, is being very supportive. I think us overhyping things too early on isn't going to help.
Yeah.
There is a long journey to go. I think most companies now in the area of solid state are saying nothing before 2025. If things do occur after that, it's likely to be supercar, hypercar for affordability purposes and also to get things onto a vehicle. So really nothing on a passenger car till the end of the decade.
Yeah.
So that's a bit of a marathon, not a sprint. If you start making noises now, you'll run out of things to say quite quickly. So I think as long as it's going well, we're getting support from the government, getting support from our investors. Our best bet is to say what we're going to do and do it. If we over-egg it, if we say too much, we'll create too much of a hype, and that's just probably not going to be helpful.
Oh, fantastic! It's really fantastic, and it's great to learn all of this and see all of this, and hopefully we'll stay in touch. And I can feel a follow-on episode in a year or two's time when there's a bit more to talk about on the particularly the large format batteries, and I really hope to see some of those micro batteries out in the market in the not too distant future. So brilliant. Thanks a lot, John.
Thank you very much. I'd absolutely love to be here in 2 or 3 years' time, as you say, talking about things inside the body or whatever has gone on next. But really a pleasure to be on your program.
Brilliant. Thank you.